Assalamu alaikum. Today we will be talking about the Q system, which is one of the different systems that are used for rock classification around the world. Previously, we have seen rock classification systems such as RMR, the RQD system, and then we saw that the Zagis Doppler system. So this is just like the system we have been previously using. The only thing different is that it is more advanced and it's quite detailed system for rock classification. So let's have a look at the system. So the governing equation is this here. You see that Q value ranges from 0.001 up to 1000, and basically it contains three quotients. The first quotient, okay, this is called as rock block relative block size, and then we have JR over JA, okay, that is the roughness quotient, and lastly we have active stress quotient, that is JW over SRF. Now what is RQD? RQD is the rock quality designation, we already know that, and JR is the joint roughness number, and JW is the joint water reduction factor, SRF is stress reduction factor, and then JA is joint alteration number, and JN is joint set number. Okay, now you don't need to get confused or panicked here because it is a very simple method. And why is it simple? I'm saying that because we have tables. You just have to look at the rock conditions for which you're going to evaluate the Q system. So you just look at the system and then select the appropriate value from the table, and you just plug in the values, and later on when you do all the maths you will have the value of Q. So let's see in detail the first quotient, that is relative block size. So some few important points for this is that if you are using our RQD value of less than 10, then we use 10. We don't use 0 because we know that if we put 0 here then our whole equation will become 0. So to use it in Q system you will only use the minimum value of 10, and also we use value differentiating by a value of 5. For example, if you are getting a value of RQD as 14, it's better to use 15 and so on. So if it should be 5, 10, 15, sorry, not 5, 10, 15, 20, 25, 30 and so on. So RQD value we have already seen in our previous lectures that you have to make a core and then count the sizes that are bigger than 10 centimeter and divide it with the core length to get the value of RQD. So we will obtain RQD from there, and JN will be obtained from this table here. So you see here on one side we have the joint set number, and then we have corresponding value of JN. So for example, if you have two joint sets, then a value of JN of 4 is to be used, and we have three joint sets, then a value of 9 is to be used. The second quotient, that is interblock shear strength, JR over JA. So it basically tells us about the joint roughness and alteration. So this represents frictional characteristics of wall, or if there are any infilling material in between the wall. So what is infilling? So if this is a joint of a rock and if it has some material in it, so this material is called as infilling material, or simply some people call that as filling also. So it tells us characteristics of both. So rough and unaltered joints in direct contact are favorable. So if we have a joint condition like this, that the joints are in contact with each other, this means that this is the best condition and they are going to give very huge strength. And then we have when clay infilling is there, it reduces shear strength significantly. So the example that I showed here, so if there is clay in between and when the rock is going to shear like this, then this is going to reduce the shear strength because the rock surface will not come in contact and clay will be making them slide between the two sides of the fracture. And then rock wall contact after small shear is also good. So that means initially we had a situation like this, and once shearing was happen, so it is converted into this form. Okay, so the moment, due to the moment these heights and drops, they come in contact, and now the walls are coming in contact with each other. So this happens after some shear, so this is also very good. So no rock wall contact is very unfavorable for tunnel stability. So if there is no rock wall in contact, that means this is one side of the wall and this is one side of the joint, and this is all containing filling in between. So this is very poor condition and it is very unfavorable. So JR will be obtained from this table. So we have different conditions. So if you have a rock wall contact or the rock contact was developed after 10 centimeters of shear, then we use this table. So if we have up to here, so if we have smooth undulating joints, we use 2. If it's smooth and planar joints, we use 1 as the value. And if the no rock wall contact is when it's coming in shear, that means it is containing filling. Then if that filling is made up of clay minerals thick enough, then you use 1, and other conditions also mentioned here. Then we see how the value of J is used, and once again, if the rock wall are in contact with each other, okay, and then if we have unaltered joint walls, surface staining only, we use 1. If we have silty or sandy clays, we use 3. Similarly, if we have rock wall contact before 10 centimeter shear, we use this table that says sandy particles clays, then we use 4 as JA. And lastly, if there's no rock wall contact and if we have zones or bed of disintegrated rock, we use 6 as the value of JA. If you're getting stressed out or confused at what's happening, how we quickly calculate these values from the table, so we will do one example. I'm sure that will get you out of oblivion, and you will be able to understand how to use this method. We will do that just in a while. So active stress quotient, that is JW over SRF. So first we'll talk about SRF. So it is the you can say that it is the total stress parameter. So when do we need to use SRF? So if we have losing load when excavation through shear zones and clay bearing rock is happening, and if we have rock stresses in competent rock and squeezing load in incompetent rock, so there we need to use a stress reduction factor. And JW, as the name suggests, is the water pressure that reduces shear strength also, and this is how we use JW. So if your joint is totally dry, we use a value of 1. If it is large inflow is happening, we use a value of 0.33 and so on. And lastly, the table of SRF. So for different conditions, so if you have single weakness zone, we use a value of 5, and if we have multiple occurrences of weakness zone, we use a value of 10. So this is how this Q system will work. We have the only thing that we need to achieve from the field is the RQD value, and remaining all of the things you have to look at the site, and then you have to look at these tables and find out the respective values of all the quotients. So eventually, once you are done calculating the value of Q, then it will fall in either of these classes, and you can see the quality. If it's between 400 to 1000, it's exceptionally good, and if it is 0.001 to 0.01, it is exceptionally poor, and so on. And so we will use this to find out you can use this chart to find out the stand-up time and the unsupported span. You see different qualities are mentioned here. So based on these, we have this table. Okay, so you can see that what value of Q should you be using, okay, and you can find out the stand-up time and the unsupported span length from here. To explain the tunnel support requirement, Barton proposed our parameter that is called as DE. We call that as equivalent dimension. So the formula of equivalent dimension is, it's mentioned here, it is excavation span or the tunnel height or the tunnel diameter divided by the excavation support ratio, ESR. So excavation span, tunnel height, so you will know that because you will be knowing how much value of tunnel you're going to design. ESR will be obtained from this table here. So if you have different conditions, if you have temporary support for mines, it is 3.5, and it is nuclear power plant, it is 0.8. So basically you will find out based on the type of construction you are using. So from this you can find out DE, and then lastly you see here we have this, let me move this extra stains here. So this is the graph that you will use at the end. On x-axis we have Q value, it ranges from 0.001 up to 1000, and on y-axis we have tunnel span over ESR, that is DE or the equivalent diameter. Okay, so find DE on y-axis and then Q, then you will use a chart, and based on where your point is falling, you will use the calculations. For example, if your zone is coming to be 3, then you go down and look that what is the value. So for a value of 3, we need to use systematic bolting with fiber concrete and 5 to 6 centimeter thick. So this is how it will work, that you simply have to look at the DE value and then look at the value of Q, and then eventually you will find out the value of the type of support required. So we will do one example now. So this example is mentioned here. So what I will do is that I will start on selecting the values. So I'll go back to the Q system here. Let me go to the top. Alright, so we have this equation here and we will start plugging the values. Let me switch my pen. So first value is RQD. So we'll see what is the value of RQD. It says value of RQD ranges between 85 to 90%, 95%. So we will use 90 as RQD. And over JN joint set number. So I'll go to that particular table of JN to see that what value should be used. So JN table, so let's see where this. Okay, so this is JN. So to find out the value of Jn, we need to see the number of joint sets. So go back. It says it has 2 set of joints. So for a 2 joint sets, we use a value of 4. So go back to the equation. So this comes to be 4. And now we see JR and JA. I'll go to the table of JR. So JR, we need to see if the rock wall is in contact or not. So go back there. So there is, in this equation, there is no mention of rock wall not coming in contact. Okay, so and then we have to see the details of the joint. So it says the joints are undulating rough. So it's saying undulating rough. So I'll go and look here. So if we have, so this looks to be the choice, undulating and rough. So this value of 3 can be used from here. Okay, so I will use value of 3 as JR, and then now look for JA. I'll go back to the table, and once again, as there's no mention of joint, so we'll assume that the joint wall is in contact. And the conditions mentioned here is that it has unweathered and very minor surface staining. So you see here, this is the option, unaltered joints and surface staining only. So the value of 1 is used. So I'll go back and use 1 in place of JA. Then we have to use JW, that is joint water reduction factor. So there is no mention of water inflow. So we'll assume our joint to be dry. So we use, you see, for a dry excavation, we use a value of 1 for JA, or for JW. So I will use 1 here. And last thing is SRF, that is stress reduction factor. So for this table here, SRF, so it says single weakness containing clay or excavation depth is less than 50 meters, and this is excavation depth greater than 50 meters, and we have an excavation depth of 2100 meters. So we will opt this value, that is 2.5 as the strength reduction factor, SRF. So I'll plug in the value here, 2.5. So let's do the maths and see how much we are getting. So 90 multiplied by 3, and then divide it with a 4, and then divided with a 2.5. So it's giving me a value of, let's check again if I'm missing something. So SRF, how much we used? 2.5. Okay, so SRF of 2.5. So it's giving me a Q value of 27. So for the example here, the Q value is 27. And then last thing is to calculate the equivalent dimension, that is DE. Okay, so DE is the excavation span. So excavation span was 15-meter span, so 15 meter comes here, and then over excavation support ratio, that is ESR. So ESR for this condition, it says water tunnels, permanent mine openings, so we will use a value of 1.6. So 15 divided by 1.6 gives us a value of 24. So we have, I write it along with the chart, DE of 24 and Q, how much was Q value? Q was 27 and a Q of 27. Now we will plot these values. So on x-axis I will look for 27. So this is the log, this is 10, this is 100, 40. So our Q, this is 20 and this is 30. So our value will be falling somewhere here, and we have a DE of 24. So 24 would be lying somewhere here. So let's see where they are intersecting. So they are intersecting in this zone. You see this zone is zone number 3, so that means we have to use the support option of number 3, and that is we will use systematic bolting and fiber concrete of 5 to 6 centimeters thick. So this is how the Q system works. You eventually have to find out DE and Q by using tables and by using your field values. Okay, and then eventually you put in the values, simply plot, look for the X and Y values wherever they are plotting, so we will know that what type of support we are supposed to use. So after that there are certain formulas. So to find out the length of the bolt required, you can use this equation, okay, where B is the excavation width and ESR can you obtain from the table, and also maximum span that can go unsupported can be found out from this ESR into Q equation. And also you can find out the permanent roof pressure P roof by putting the value of JN, JR and Q to find out P roof. So after this, the next system that we'll discuss today is the Gsi system. It was developed by Hook in 1994. It is quite simple and easy system, okay. It was initially just for the evaluation, but later on it's also became used for the evaluation, rock evaluations. So these are the 4 categories in which the Gsi system is divided. So here is a comparison between the joints volume and the RQD value, and it is a detailed table. So on y-axis we have the condition of the rock, that is blocky, very blocky, folded and crushed, and on x-axis we have the decreasing of the surface quality. If you have good quality, fair, poor, very poor, and if the joint so very good is very rough, fresh, unweathered joint surface, okay. So similarly you have to look at the joint condition, and then you have to look at the overall rock condition, that it is falling in which category, blocky, very blocky, okay. And then we can finally find out the GSI value. If it falls between 75 to 95, then it's this. So it works in the similar way. You see, you will look for the quality from here and here. So wherever it is falling, for example it's falling in 40, then we have this option, that is a fair quality rock. So this is a very simple and easy system, but you have a lot of variation because different people do different observations. So GSI would end up having more variant values depending on the person taking the reading in the field. There are some very important correlationships. Sometimes they pop up in quizzes and maybe in your exams when you go for a job, or maybe in vivas, so you have to remember them. So RMR, this was the system we used in our previous lecture, rock mass rating. So it is 9 log into Q. This is the Q value we just learned, and A is a parameter having value of 26 and 62, and 44 is the average value. So plug in the values. So if you know your rock quality by Q system, so plug in the values and you can find out the equivalent RMR rating for the same rock. And conversely, if you know the RMR value for your system, you can find out the Q system by plugging in this equation. So here's a comparison chart. And then once again, the other method is RMR, where we have another equation like this, 13.5 into log Q plus 43. And with the comparison of GSI, for generally competent rock masses with GSI greater than 25, the value of GSI can be related to rock mass rating as follows. So this only works once GSI is greater than 25. So there are 3 problems mentioned here, so you should go through them. So if you have any trouble or any questions regarding these problems, so we can discuss in our next lecture. Thank you very much. That's all for today. Assalamu alaikum.